Hello, this is Mrs. Taylor, and I am going to walk you through how to estimate the area under a curve using rectangles. And what you'll see is this will be abbreviated as RAM, which is the rectangular approximation method. And this is really a building block working towards the theory and concepts behind integration. Derivatives are related to slope of a curve, and integrals are related to the area under the curve. And so eventually this will become a limit, and then that will become the integral. So just a heads up of where this is headed. So if you're watching this video, you should have already worked through this activity I gave you in class, and I just want to kind of highlight some key points that are really important here. I know a lot of times you might skip the introductory paragraph of something your teacher gives you, so just want to draw your attention to some things. The idea of accumulating change is closely related to the problem of finding areas under curves. And so integration focuses on this accumulation of change. And so some things that this could relate to is if you're looking at a accumulation of change in a temperature or in money, and then also the idea of, these curves in this area, there are ways that we can then expand that to finding volume of an odd-shaped solid. And again, it's the accumulation of the change under the curve that gets you there. So that's why this is so important. Our goal is to find the area between the graph of a function and the x-axis between two specified values of x. So really, that is what integration is. Ultimately, you're just finding the area between a function, the x-axis, and two x values. So it really boils down to that one main idea. Something that's really important that you may have just kind of glossed over is the idea of an overestimate and an underestimate. So if your rectangles completely cover up the region, it's an overestimate. If they're completely contained within the region, it's an underestimate. And the more we practice this concept, the more you'll learn there is a direct connection between concavity and whether you are connecting your rectangles on the left side, the right side, or the middle. And so you will eventually see questions where you have to consider those things and just know if it's an over or underestimate without drawing the rectangles. So just giving you a heads up there. And then lastly, something I kind of want to point out, it says we can refine these estimates using a process of successive approximation similar to our approach for finding slopes of tangent lines. So this goes back to the idea that the slope of a tangent line is arrived at by taking the slope of a secant line, which is 2 points, and moving those points infinitely close to one another. And so with integration, it's the idea that yes, there are only 4 rectangles that we drew in this activity, but if we continue to add more and more and more rectangles, we get closer and closer and closer to the actual area. So we're going to look towards putting an infinite number of rectangles under that curve to get the exact area. So there's just some key points that I wanted to make about this activity, and we'll come back to it in just a second. First, my goal is to kind of give you an overview of the rectangular approximation methods, sort of just to front load some key points. So you have 3 choices for your rectangular approximation methods. You can have what we call LRAM, RRAM, and MRAM. And LRAM means left rectangular approximation method, RRAM means right, and MRAM means midpoint. And so all this is referring to is where does the rectangular connect to the curve. So does it connect to the left of your subinterval, the right of your subinterval, or the midpoint of your subinterval? And so just to give you a visual of what this looks like, on the activity you completed, the first set of rectangles you drew, that was an example of RRAM because each rectangle connected to the right. If you wanted your rectangle to be 1 unit wide, you would go to the x value that was on the right of each rectangle and connect to your curve where that x value intersected the curve. And so this is RRAM because the rectangles connect on the right. And then for the next set of rectangles, it was an example of LRAM because if you wanted to, for this curve, have all your rectangles completely enclosed in the region, you went to the left side of each rectangle. At those x values, that's where you connected to the curve. So for the second rectangle, you would have connected where x equals 1 intersects the curve and just drawn your rectangle over from there. So this is an example of LRAM. And in the activity, you didn't complete MRAM, but just to give you an example of what it looked like, I will show you this. So to start with, for a MRAM, I need the midpoint. So if I was going to draw a rectangle in this first subinterval here between 0 and 1, I would go to the middle x value, which would be at 0.5, and that is where I would connect to my curve. So that's what that point represents, is the height of my rectangle. So if you drew a horizontal line through that point, that would create your first rectangle for the midpoint rectangular approximation method. And if I continued that pattern, I would continue to mark the midpoint of each subinterval, each rectangle, and that would become the height of the rectangle. And then I would, like before, just do base times height for each one and add up all of those areas. So that would be midpoint rectangular approximation method. If you boil down what we just did into just like a quick reference guideline of what each of these means, if you think about it conceptually, RRAM, when you are finding the height of each rectangle, basically means you skip the first y value. So if you think about that in the context of the activity we just did, I went to the second, I'm sorry, that's not it. It's skip the first x value, sorry. So instead of connecting on the left, which would have been the first x value, we connected on the right, which is the second x value. For LRAM, that basically means you skip the second, or the last x value. So if we're connecting on the left, the very last x value would be left off. And then MRAM, of course, you don't get to skip anything, you have to do extra work. So you have to calculate the midpoint. Then use that x value to calculate the corresponding y value, which gives you the height of your rectangles. So more work for the midpoint, which is why a lot of people don't want to do it. Alright, so just some more front loading of information. They're going to give you a width or base of each rectangle. And so a lot of times it's consistent. So I just want to give you a quick way to find it. So the base of each rectangle is the distance between your x values. So in your activity it was 1. That's the base of each rectangle because that's how far apart your x values were. Sometimes you'll be given an interval and a number of rectangles. And so in that case you can find the base really easily. So basically what you do is you take your two x values that define your interval, subtract them, and then divide by the number of rectangles. That divides evenly the distance from beginning to end. So algebraically it would look like this. You have your interval from x1 to x2. They give you a number of rectangles, so you subtract the x's and divide by the number of rectangles. And this gives you the width of each rectangle. So in the activity you just completed, the interval for number 1 would have been, or for the first page, would have been from 1 to 5. And there were 4 rectangles. So 5 minus 1 is 4. 4 divided by 4, 1. So you get the width of each rectangle that way. Sometimes they won't give you a graph. Sometimes they'll just give you an equation and a number of rectangles and an interval. And so to find the width of each rectangle, you do what I just said, use that little formula. But you also need to find the height. So the way you do that is you first determine your x values. So if it's RRAM, leave the first x value off. If it's LRAM, you leave the last x value off. And if it's MRAM, of course you have to calculate the midpoint of each rectangle. And then you substitute the x values into the equation for the height of each rectangle. And so you don't really need the graph if you have the equation, but sometimes the process can seem a little harder because visually you have no confirmation of what you're doing. But this is just a really quick summary of the steps you would take. And then the last just front load of information is just a word of caution. Sometimes the bases of the rectangles won't be consistent. So AP loves throwing that at you where you're so used to each rectangle having the same width that you don't really pay attention. So if that's the case, just be careful and don't assume that the widths are all the same. And we'll look at examples like this in class, so it'll make more sense once you see an example of what I'm talking about. So again, this is just front loading some information. As soon as you get in class, we'll hit the ground running with some examples, and I'll refer back to this information to put it in context. But I wanted to give you a chance to get this down in your notes so you'd have it to reference while we work through examples in class.